All right, good morning, class. We're going to look at chapter 4. We're going to start looking at detailed drawings. So actually putting our parts that we've modeled onto drawings. So this will be the first part of the chapter. So we'll go through the presentation, and then we'll have also the videos on the tutorials of the parts, and everything will go along with the assignments. And this will be for the first part of the book. So the housing, side cover, and top cover. So with the housing, you're going to learn how to add part configurations, suppress certain features, configure dimensions, make a new drawing, and you'll add different views. You'll see how simple this can be. Put in a section view and a detail view, import model dimensions, add a drawing sheet, and then add layers and move annotations to it. On the second one, the side cover, you'll look at adding configurations, again, suppressing features, configuring dimensions, making the drawings, adding views, putting in an aligned section view, importing some dimensions, adding a drawing sheet, and then changing the view's configuration. And then on the top cover, we'll look at making the drawing, adding section and detail views, import and arrange dimensions, add ordinate dimensions, add notes, part custom properties. You'll look at adding custom properties to the notes, and then add a layer, and then move the annotations to it. So first we'll look at some dimensioning standards. So accurate dimensioning is one of the most demanding undertakings when designing parts. You want to use a checklist to ensure you have followed basic dimensioning rules. But keep in mind there may be a case where you need to break a standard to give clarity to the part and the manufacturer. We looked at this in the beginning of the semester. So in order for the drawings to be dimensioned so that all people can understand them, we need to follow standards that every company in the world must follow. Standards are created by these organizations. We looked at ANSI, ISO, DIN, JIS, MIL, DOD, and CEM. ANSI is the American National Standards Institute. This institute creates the engineering standards for North America. ISO, the International Organization for Standardization, is a worldwide organization that creates engineering standards with approximately 100 participating countries. And these will be the biggest two standards that you will see here in the United States. DIN, this is the German Standards Institute, JIS, the Japanese Industrial Standard, and then CEN is the European Standards Organization. The United States military has two organizations that develop standards, so if you're doing anything for military, you'll see either DoD or MilSpec standards. So linear dimensions are comprised of four components. We have our dimension lines, our dimension text, our extension lines, and our arrowheads. So the extension lines, we want those to continue 1/8 of an inch past the dimension line. SolidWorks is going to automatically take care of most of these for us, but we do want to understand these rules. That way if something is out of place or we do need to make some changes, we'll at least understand where they come from. They are extended from the view to indicate the edges referenced and hold the dimension line. You also want it separated so that they don't look like they are part of the actual part. Right there, so the 1/16 inch gap, so they're not confused with visible lines. We have horizontal dimension lines. We have aligned, so you can see the 1.80 there is aligned with this angular surface. Vertical, so you can see this is vertical. You can also have aligned vertical when you're using ISO standards. When dimensions are stacked, they are 10 millimeters or 0.4 inches from the view, and 6 millimeters or a quarter of an inch. Arrowheads, these are the typical dimension line terminators. There are other acceptable dimension line terminators like dots or datums, just depending on your company standards or whatever they're using on their basic templates. Arrowheads point directly to the object that is being dimensioned or the extension lines at the end of the dimension. They are made 3 times as long as they are wide. Dots, so oblique or architectural ticks used in architectural drawings. Those would be like the big differences you see. Dimension text. So if the dimension text will not fit between the extension lines, it may be placed outside of them. Dimension text is placed in the middle of the line, both horizontally and vertically. Dimensions are represented on a drawing using one of two systems, so unidirectional or aligned. The unidirectional method means all dimensions are read in the same direction. It means they'd all be horizontal, and most of the time. The aligned method means the dimensions are read in alignment with the dimension lines or side of the part. Some read horizontally and others read vertically. And these are going to go by different standards. So usually the unidirectional will be ANSI and the aligned will be ISO standards. We're going to want to make our drawings based on ANSI standards. So we'll want everything unidirectional. So when you're doing your drawings, if you come up with dimensions, if it starts to place dimensions that are aligned, red up and down vertical, you'll just want to go into your options and change your standards from ISO to ANSI. Unidirectional dimensions are placed so they can be read from the bottom of the drawing sheet. This method is commonly used in mechanical drafting. Aligned dimensions are placed so the horizontal dimensions can be read from the bottom of the drawing sheet, and the vertical dimensions can be read from the right side of the drawing sheet. So you can see the unidirectional dimensions. Everything is the same, right? They're all horizontal pretty much, or exactly on this one. And then the aligned has horizontal for the horizontal lines and then vertical for the vertical lines. There are two classifications of dimensions, so size and location. And if you'll remember when we first started talking about fully defining a feature, right? These are the two things that SOLIDWORKS looks for. So the actual size of the feature, and then where that feature is in relation to our datums or to our origin point, right? So it wants to know where in space that is. So those would be our two types of dimension. Size, the dimensions are placed in direct relationship to a feature to identify the specific size. And location, the dimensions that are used to identify the relationship of a feature to another feature within an object. So maybe this is a hole from another hole, or a hole from the side of the part, or a cylindrical feature, and where that might be on the part. So the dimensioning checklist, so each dimension should be written clearly with only one way to be interpreted. A feature should be dimensioned only once, and SOLIDWORKS does a good job of telling you if it's over dimensioned. Dimension and extension lines should not cross, although you'll see on some of these drawings, sometimes this can be impossible. Each feature should be dimensioned, so you want to make sure that everything has a dimension to it. And dimension features or surfaces should be done to a logical reference point. Dimension circles should have diameters, and arcs should have a radius. So if it's a complete circle, you'll have a diameter. If it's not a complete circle, you'll want to dimension it with a radius. You want to locate dimensions near the features they are defining. A center line should be extended and used as an extension line. So if you have a part where you have a mirror or you're showing a center line, you want it extended through the part. We looked at this when we looked at in the beginning when we had center lines and how they were placed on holes and things like that. Dimension features on a view should clearly show its true shape. So you don't want to dimension something that's not on the view that you're actually looking at it. Right, so we looked at, angled features, right? So if you're looking at a foreshortened view of it, you don't want to dimension that view. You don't want to dimension the side view of it so somebody can see the true dimension of what they're looking at. And enough space should be provided to avoid crowding and misinterpretation. Extension lines and object lines should not overlap. Dimensions should be placed outside the part, so you do not want any of these over the top of the part or on the part. Center lines or marks should be used on all circles and holes. Align group dimensions so they are neat and easy to understand. You want to locate shorter dimensions closer than larger ones. This helps to keep lines from overlapping. And do not dimension the same distance twice. Linear dimensioning, so dimensioning from feature to feature is also known as chain dimensioning. It is commonly used and easy to lay out. It does have possible consequences in the manufacturing of a part. Tolerances can accumulate, making the end product larger or smaller than expected. And we're going to look at linear dimensioning, although it's not really used anymore, especially in manufacturing. So it may be used in some, different types of drawings, outside of the manufacturing environment. But with the new geometric dimensioning tolerancing standards, they've gotten away from linear dimensioning, and we'll look at datum dimensioning here in the next one. But I just want you guys to understand, what linear dimensioning is. So here we have chain dimensioning. So we can see this is a general note, indicates that all two-place decimal dimensions have a tolerance of plus or minus 0.01 unless otherwise specified. So we can see our chain dimensioning here. So 0.5, 0.5, 0.5. So if we use our tolerance that we have down here, each one of these steps can range between 0.490 inches and 0.510 inches, right? So we could have 0.510, 0.510, 0.510, and this would add up to make the part 0.3 of an inch bigger than our nominal dimension, right? So we see the chain dimensioning layout can have an effect on the final length of the part, ranging from 1.47 to 1.53. And typically, if we have two decimal place, this part, if these are our nominal dimensions, this would be 1.49 to 1.51. So you'd have this overall dimension on the overall distance of the part, which typically would put this part out of specification overall, even though every single one of these features would technically be in specification. So you want to place an overall dimension. This will limit the chain effect on the tolerance buildup. The accuracy of the final product is determined by the dimensions of the drawing. If all the dimensions originate from a common corner of the part, the object will be more accurate. This is referred to as datum dimensioning. Datums ensure that tolerance or errors in manufacturing do not accumulate. Right, so they'll have the dimensions will originate from a common edge, and sometimes even on drawings now they'll put this as datum A, datum B, datum C, and what this does is, one, it tells you the reader where these dimensions are originating from, but also two, if you're in the quality control department or in the lab or testing the specs on a part, you'll know where to start measuring that part from. So when you say part A on one side, that'll be the first part or the first side that you'll actually put into your measurement device. So you'll know which side to line up first, then your second side, then your third side, and you'll know exactly how to put this part in. Without really knowing the total design intent, you'll know exactly how to measure this part and be able to tell if it's in specification. So the dimensions originate from a common edge called the datum of the part. Again, we have our general note. So here we can see that this step, can be 0.490 to 0.510 wide, but now we can see the total distance can only be from 1.49 to 1.51 wide. So each one of these is going to have its own tenth of a millimeter or hundredth of an inch tolerance, right? So this will have its own plus or minus 0.1. This section will have its own plus or minus 0.1, and this section will have its own plus or minus 0.1. So here's some of the dimensioning symbols. So the degree symbol, reference symbol. So that's put around usually a dimension. If it's just a reference dimension, you're not actually using it for go no go or to test the tolerance of it. Diameter symbol, radius symbol, counter bore for some of the screw holes, countersink, same thing. Depth or deep symbol. So this will usually tell you on your countersink, you're going to go this depth, this width at this depth for a certain length, and then it'll go, the rest of the screw will go through. Places or by symbol, plus or minus symbol on tolerancing, centerline symbol, square shape symbol, arc symbol, and then a slope, which would usually come into a lot of civil drawing. Dimensioning angles. So angled surface may be dimensioned using a coordinate method to specify the two location distances of the angle. Angled surfaces may also be dimensioned using the angular method by specifying one location distance and the angle. So here's the coordinate method. So if you're going to put it in chamfer, right, you can go into your chamfer tool and put in these same dimensions, and it'll give you these same options to put in this angle. Arcs and circles. So they're dimensioned in views that show the true shape or show the arc of the circle. They're dimensioned with a leader to identify the radius. In some cases, a center mark is included. That's pretty much standard now, so almost always a center mark is going to be included. So again, with the new geometric dimensioning and tolerancing, everything is going to be measured to the center mark. We can go into a whole lot of reasons why, but we can do a whole semester on just GD&T. But just know that they'll have a center mark there, and that's typically where any type of circular feature is going to be measured to. Circles should have a center mark in their dimension with a leader to identify the diameter. So the arrow can be inside for small arcs. You want to use a capital R for dimensioning arcs, so you're showing a radius. Large arcs use a center mark, and then small arcs do not need center marks. The arrow can be outside. A full circular object should be dimensioned using its diameter. Holes should use hole notes. So here we see the diameter of 50 for a depth of 1. Specification calls for a hole with a 0.5 diameter, 1 inch deep or 1 unit deep. And there we can see our radius of 0.50 outside, and then our center to center. Cylindrical parts may show their diameters in this manner. Dimensioning on the right side view may be too crowded. So you can see, instead of showing all the diameters how you're out here on the right side view, we could show the overall diameter on the front view or left side, however they put this in. Note that the diameter symbol is used so it is not confused with a linear dimension. Chords, so they may be dimensioned in one of the following ways. So you can either show the angle or the distance. Dimensioning curved features. So points are placed along the contour and are dimensioned from the datum, and you can see they're showing the distance from the datum as well as reference dimensions for the height. Reference dimensions, this designates more than one of the same feature. In this case, is identifying there are 2 identical holes. So you can see this says 2 times diameter of 0.25 through, and they give their countersink measurements there. So just diameter of 0.38 for a depth of 0.25. Chamfers, external chamfer for 45-degree chamfers only. So there are 2 options. You could say 45 degrees by 0.125 or 0.125 by 0.125. External chamfer for angles other than 45 degrees, so you can put the angle in and show the distance. And then internal chamfer, as you can see, they're showing the total distance and then the angle for the chamfer. Fillets and rounds, so you can see the small fillets, they just have a leader going to it. For the larger fillets and rounds, they have the center mark. Center mark, small arcs do not. Conical tapers, so you'll have your 2 major dimensions, your height, and then an angle. Slot dimensions, so the 2 methods shown on the left are the acceptable methods for dimensioning slotted holes. So you can show the overall length, or you can show the center to center. With 2 times, you can have your 2 times your radius. This will probably come back to, however you draw this on your sketch. And that will also, go back to the design intent of this. So, again, if it's more important to know where the center marks on these holes, which is usually the case, we'd put in our center to center dimension. However, if the outside dimension is what was really important, that's when we'd use that outside dimension versus our center dimension. Dimensioning radial patterns, so angles and radius values are used to locate the centers of radial pattern features, such as holes on this plate. So you can see the angular features and then the radius for the center of circle centers, and then the diameter of the overall circle. Keyways and key seats. So this is a keyway, and we've done a part with this. And then a key seat, we've also done a part with. So you can see on our shaft how they've dimensioned their tolerances there. So 0.126 and 0.125. They're showing their center at 0.063, as well as the tolerances for the height of it from the bottom. The keyway dimensions, so again, they have their maximum, minimum keyway dimensions, also from the center, and then the height of the keyway from the bottom of their circle. Hole dimensions, so holes are specified with numbers and symbols. So there we can see the diameter of 0.25 at a depth of 0.75. That's going to be our inside hole. The countersink here, so you see the countersink symbol. is going to have a diameter of 0.38 with a depth of 0.25. This hole will just be a diameter of 0.38 with a depth of 0.5, and this hole will be a diameter of 0.38 all the way through the part. So here we see the hole diameter is 0.25 inches and will be drilled 0.75 inches deep. The hole will be counterbored to a depth of 0.38 inch diameter to a depth of a quarter of an inch. So there we see our counterbore or spot face symbol and our depth symbol. This hole diameter will be 0.38 inch drilled 0.5 inches deep, and this one will be 0.38 inch all the way 0.38 inches all the way through the block. Reading thread notes. So threads are dimensioned with the use of local notes. We will discuss the two methods, so ISO and the Unified National Thread method. So the major diameter, we see 5/16 of an inch. We see 18 threads per inch. And this identifies coarse or fine thread. In this case, C for coarse, and F is for fine. So we'd say UNF if it was fine. ISO thread notes, so we can see M is for metric. Or we have our nominal diameter in millimeters, so 12. Our pitch of the threads. So if you remember from chapter 3, we actually learned how to put in pitches on our threads. The 6/8, so this number can be 3, 4, 5, 6, 7, 8, 9. It is the grade of tolerance in the threads from fine to coarse. The H is for the allowance. G would be a tight tolerance, and H is no allowance. Prior to through, you may have an LH for a left-handed thread, and then finally, so through, or if there's a depth, if it's 20 millimeters or 30, that would be specified. This is going to be the drawing layout, so this is going to be typical, right? Although this is a very basic and simple part. So, you know, if we have a part where we need to cut through and so show a section drawing, we'll do that. But if we're just doing a basic drawing, so this is just the template we want to use, something like this, right? It can be a little different. I just want you to notice that we have our drawn in here, so you can put your initials in here, what date you did this. Your title is going to be just like your file name. So this will be O. Simpson test block. And that's the same exact file name I would use to save this. So when I draw this test block, I would say O. Simpson test block, and it would say .SLDPRT. Or for my drawing, it would say O. Simpson test block dot, the drawing file name. So, and then my drawing number, so this is 319, that's just going to go with whatever it is. So if it's like chapter 2, drawing number 8, let's say 2-8. We want to just make sure all this basic information is in there for the drawing. So that's why I included this template for you so that you guys can set up your drawings. So the ones that aren't specified in the book will be on something, you know, basically like this type of layout. Or, you know, you set up a template in the beginning. Well, I take that back. That was just for the SolidWorks setup. So we'll use something just like this, and as long as it has this basic information on it, you know, we'll have everything you need. If you want to, you know, add some more to it, you know, feel free to do that. So this is everything for the first part of chapter 4, and I'll get the videos up for you as well for these first 3 drawings, and then let me know if you have any questions. All right. I hope you have a great day. Sorry about the coughing on here. I guess the allergies got to me today. All right. I'll see you all in the next one.